about CXL-based memory for dynamic Keiko maintenance in large-scale crafts. So this presentation is divided into 5 sections. First section will discuss about the problem. Then we will discuss about the proposed hardware. Then we will see from the literature review what we learned about the potential implementation. And then we'll discuss about our preliminary implementation and experiments. And then we will discuss about the research proposal. So before diving into the problem, we have to know what K-core is. So K-core is the maximal subgraph in which every vertex has a minimum degree of K. So in this graph, if we consider A, B, C, D, E, F, then it's a 3-core graph because every node has a minimum of 3 degrees. And then if you consider G, it will be a 2. And if you consider H, then it will be a 1-core graph. And since we are planning to do dynamic K-core maintenance, we need to understand the challenges about the dynamic graphs. So basically, a dynamic graph is a graph which is constantly evolving. So every time if a node or if a vertex is added or removed or updated, it creates a ripple effect throughout the graph. And to know that exact result, we have to check the whole graph or maybe check the affected nodes to see what has updated. And then we have another challenge, which is the scale. So the graphs are actually getting bigger every day. So if you consider like social networks or maybe computer networks, every day thousands of posts or maybe nodes are being added, and the graphs are getting so big that we are not comfortable to analyze them in like plain old DRAM. So to analyze the graphs, we have 3 approaches for now. So the approaches mean the level of hardware or the kind of hardware we use to analyze these graphs. So first we have the DRAM. So we have pros and cons of everything. So the DRAM is extremely fast and it's reliable. Some DRAM also can come with ECC, which helps these operations a lot. But the con is the DRAM is volatile, which means it can't keep its data if a power loss happens. And it's also very expensive. And the storage is also, the capacity is also limited because a CPU can handle a certain amount of DRAM at maximum. Then we have persistent disks. The persistent disks is like as it named, it's persistent, means it can retain its data and it's very cheap, so it can have large capacities. But the downside of the persistent disk is like it's very slow and it only allows sequential reads and writes. And then we have complicated hybrid systems or distributed systems where multiple machines come together and share its resources to like solve the issues we mentioned earlier. But the biggest downside is they are very complicated to handle. They are highly complex and requires a lot of maintenance as well. Also, it's also synchronized to like sync all the data and keep them coordinated as well.
Question. How the algorithm can run on SSD? This is a persistent disks.
Yeah, the algorithm can't run directly in the SSD. That means that the algorithm is pulling the data directly from the disk.
Yeah.
So
Does it need memory?
Yeah, like the algorithm itself will be running in the memory, but the data is in the disk because you can pull the whole big graph into the DRAM.
Oh.
So these pros and cons have some costs. So the here are some costs we have mentioned here. So the DRAM is smaller, so we can fit large graphs. So that's the cost we have to pay if we go with the DRAM. Then for if we want to analyze the large graphs in persistent disk, it can take up to 64% of execution time due to serialization and deserialization because you have to write data in such ways. And then setting up the distribution system, we already discussed it, like it's very costly and it's not efficient.
Here, why is the distributed system not efficient?
Because to read and write data every time from a disk, you have to either to read it, you have to deserialize it, or if you want to write it, you have to serialize it.
Serialize. What's the mean of serialize? What do you mean for serialize? Can you explain?
So basically, what happens that you can just save, like for the algorithm, we have a data structure. Suppose a hash map or something. So you can just put the data directly into put the hash map directly into the storage disk. You have to serialize it as a file, then you have to store the file into the disk. That's why it's very expensive operation, which costs around 60% of the execution time of the whole algorithm.
Okay, good. Because most of the time is to spend on, the network communication.
Yeah.
Network communication, the distributed system, all of the clients are connected with a network.
Yeah.
And the other time is spending for synchronization.
Yeah.
Master communication.
Yeah.
So it's master slower, but it can handle much larger
graphs.
Yeah. Go on.
Okay, so now we have to see what's our proposed solution is. So for the solution, we proposed persistent memories. So entire persistent memory. Currently, we can think the whole persistent memory generation into two generations. First, we have the octane-based persistent memories, which were created by Intel. So Intel-based persistent memories are basically directly attached to the DIMM slot of the motherboard. So here you can see in the left side, the PMs are actually connected in the memory slots. And then we have the current rising architecture, which is CXL-based memory, which is connected via PCI Express slot. And it actually frees up the memory slots. So the same machine with CXL-based memory can have greater memory capacity because it doesn't occupy the memory slots. And you might think that since it's using PCI Express, it might be slower like SSDs, but it's actually using the same link as the graphics card uses. So the bandwidth is actually very good, and we will be seeing this in details in our experiments as well.
How about the performance? Similar?
Yeah, performance is compared almost similar, but it has the latency for Optane base is like sort of fixed, but depending on the CXL memory and which PCI link it's using, it can vary a bit. Like all the Optane memories have similar latency, but CXL base can vary depending on the PCI Express link or how it's created. Oh, sorry. Okay. Why why we think persistent memory is the solution. So persistent memory is byte addressable. So we can actually address individual bytes of the memory with our C++ codes. Then it's persistent. That means that if a power loss happens, the data won't be flushed. And it's faster than hard disks and SSDs. And it has the scale or the capacities of persistent memory are larger than DRAMs. Also, because of all these features, it can allow instant recovery of data. So then we have the drawbacks of the persistent memory. It's not always sunshine and butterflies for the persistent memories as well. So the biggest issues of the persistent memories are its writes are slower. Since it has to write a 256 bytes for even if it's writing a single byte, so the write latency is greater than DRAM. Then we have high consistency overhead. Since it's persistent, CS is persistent memories has to write every data as a transaction. It means every byte is atomic, and this atomicity costs us some performance overheads.
Here, do you think it's so every operation is atomic? You mean?
Sorry?
Every operation writing to the PM is atomic, or some necessary scenario we need to be atomic?
It depends on what we are doing. Like if we are using the PM as a generic platform between RAM and storage, as it's just generic, like the software or the application we are using is not optimized for PM, the writes will be atomic. But if we use like dedicated application for PM, then we can actually manage which writes will be atomic and which writes will be.
So in database, in some of you have the transactions.
Yeah.
That must be atomic.
Yeah.
But other kind of application don't have transactions.
No.
For example, for our application doing.
No, we don't need to be
we don't need
for our initial purposes, we don't need it to be atomic, because for now we are only focusing on the performance of the graph operations. So if it doesn't have state of the art crash recovery, it won't hurt us for now. So then we have the costly in-place updates. So that's another downside of the PMs. So if we write the same block over and over again, it gets expensive because it has internal buffering, cache line flushing, and wire level protection. Since it's not like hard disks, so it has to ensure the wire protection as well. Okay, let's see some data from the papers we reviewed. We just aggregated all the data into digestible graphs where we can see the impact or the characteristics of persistent memory in general view. So for the first graph, we have a DRAM versus persistent memory latency chart, where we can see the read and write of DRAM has significantly less latency than persistent memory, which is expected. And in the second graph, we have various access pattern, and we demonstrated its write latency. So
what is in place update?
in place update means we are updating the same block again and again.
Modify.
Yeah, modify. So we can see the sequential writes and the random writes are acceptable, but the in place update is very like bad.
I guess here the sequential write should be writing to a empty block, right?
Sorry?
Sequential write.
Yeah.
Write to an empty block.
Yeah. We are just like appending data in sequential.
Okay, good.
But in place updates, we are maybe shifting the whole block to like left or right. Suppose if what we have to do in a CSR, maybe if we update a CSR.
So what if you have a shifting? In place update have shifting?
Yeah, because if a data is there and we need to shift it to the right.
Are you sure?
Yeah, we will see an example of this in place right in a future paper.
Okay.
We'll come to that.
Yeah.
And then we have the bandwidth against the DRAM. So we can see the local DDR5 memories are significantly faster. And then we have DDR4 and a CXL based DDR4.
Megabytes per second. Good. Okay.
So we can see the CXL bandwidth is comparable to the DDR4, and it's like very good. If we compare it to a normal SSD, Gen 3 SSD, it's like 3 times faster than a it has 3 times more bandwidth than a Gen 3 SSD.
It's a 21, sorry, it's a 21, that means it's a 21 gigabytes.
Yeah, 21 gigabytes per second.
It's really good.
Okay, so this performance is taken from the DGAP paper, and here also we show the performance of PM, where the baseline is DRAM. So we can see like it's also expected various graph performance in various PM based frameworks. They can vary up to 6 times to 1.4 times of the performance of DRAM.
So what is X? X is P.
X means like the other competitors.
Disk hybrid. Yeah.
Yeah, these are frameworks which the DGAP paper used to compare its performance.
Good.
So these are the data we found in the papers. Now let's dive into the papers, what we found. So for this reading course, we analyzed some very great papers, and we saw the pattern. We saw a pattern, how we can get around the problems of PA, persistent memories. So first, we check the DGAP paper, which is by far one of the most interesting one. So here, DGAP is a framework which allows graphs to use the PM, and it has an interesting take on solving the PM problems. So basically, DGAP introduces multiple logs. So it has logs in the DRAM, it has various logs in the PMs as well, and it has also applied logs for crash recoveries. So, so the main interesting part of the DGAP is it applies mutable CSR for the per section edge logs, and the two important logs of this framework resides in the persistent memory. So what it does,
Hey, here. Go back. So go back. So do you mean how is it this solution can solve the right amplifier?
Yeah.
You said writing 4 bytes trigger 1 block back.
yeah,
How this solution can solve this problem?
okay,
How this solution can solve this problem?
okay. So it employs two logs in the peer.
The log is in PR, but still the log still need to write into PR.
Yeah, we are getting to that. So the initial vertex array, which updates the log, resides into the DRAM. And then we have the PM, where we have the edge array and per section edge log. So the DGAP actually makes a compromise, which is we are writing into the per section edge log first. So it's mostly a sequential write. We are just adding the data.
Oh, using this log is to avoid the in-place write.
Yeah,
It's apparently
Yeah.
fast.
it's the log only it's only there to avoid the in-place write, and we are just appending the data into the logs. So we are appending the data into the logs, and then when the logs are getting full, we are merging everything into the edge array. So we
Merging have the in-place write.
yeah, but since it's not a small write, it doesn't impact us that much.
It's a block by block.
Yeah, it's block by block, and uh, this like periodical merge actually avoids the in-place write issue, but it also compromises that one thing, that there are small sequential writes happening consistently in the PM.
It is a parallel. So it's a writing thread. It has so many writing threads.
Yeah,
How
but
many threads it can support?
it's actually depending on the algorithm we are running into the framework. Like we can.
I mean the hardware. So it's PM.
No, I think that's the right thread is the CPU thread.
CPU thread.
Yeah.
So, for example, CPU have 64 cores, so it can support 64 threads in parallel.
Yeah. So this is how like DGAP makes like small compromise, but it gets on the biggest hurdle. And then we have the XP graph. It's also mentioned in the DGAP paper, this framework. This is kind of similar to the DGAP, but what it does, it doesn't create any like logs into the PM. Instead, it creates small logs into the DRAM based on its vertex, and then when a 256 byte is getting full, then it merges it into the persistent memory. So this framework is avoiding what compromise DGAP made by just writing everything into the DRAM. And then we have another hybrid approach where the framework actually exposes an API to the application. And the application thinks that it's writing the data into the PM, but instead it's actually writing in small chunks in the DRAM, and then the engine is actually merging everything back to the PM. So this framework is called PMSE, and it's also doing the same thing, like, but in a very generic way, where applications can take advantage of the framework and do its work. It doesn't have to know what's going on or what's being there. It's just doing its work, and the engine is basically doing all the heavy lifting, putting all the stuffs from DRAM.
So this paper is use the DRAM as a buffer.
Yeah.
Where is the buffer?
So
where's the buffer located?
So this is the buffer. So
This is the buffer.
yeah, it's VS.
Oh, this is physical memory.
Yeah.
This is the buffer.
This is the
DRAM buffer.
Yeah, the VSMC means virtual storage class memory. So it's just a virtual PM inside the DRAM.
Oh, okay.
So the application thinks that it's writing on the PM, but it's actually writing on the DRAM, and then the PMAC brings the whole data to the persistent memory.
So this is the buffer. It's in the P. It's in the
DRAM.
DRAM. Okay. Do you think this can be used to research this buffer strategy?
Yeah, like the papers we discussed earlier all indicates to the same solution. Use DRAM as a buffer.
Yeah.
So that's our potential solution we can apply to get around the issues of persistent memories.
Good.
And finally, we have another paper where they mention about wave source nodes. So it's a paper, it's IO efficient core maintenance in large graphs. So most of the things does not apply to us that much, but this concept, the wave source node, is a bit interesting, that we don't need to think about all the nodes in the graph for a dynamic graph. We have to consider only the wave node. Like if a node is updated, then it creates a ripple effect. It helps other nodes to increase its core numbers.
What is the wave source node? Do you invent this concept? Oh, with the wave source node. Oh, it's in this paper.
Yeah.
Okay.
So we are just considering this part, that this part might be helpful to make the K-core maintenance efficient in PL. That's a consideration. After reviewing the papers, we decided to validate the data of those papers and write our own experiments. So for our experiments, we create 3 benchmarks. One tests the instant recovery of the persistent memory. The second,
what is instant recovery?
Yeah, we are coming
later. Okay, good.
Then we have the latency test. We are just running a BFS algorithm and just calculating the time for the pointer chasing. And then we verify the right amplification issues of the persistent memory. So we don't have CXL with us right now. We actually use the Intel Optane as a proxy. Since they are in similar class, the data should be about the same. And this is our data set. We use 4 graphs.
Your graph is, which one is largest graph? I guess the first one.
Yeah, so the ORCUT and the Live Journal, both are the largest. One have much more nodes, one have much more edges.
How many gigabytes it has?
I didn't check the size.
I guess it's less than 1 gigabyte.
Yeah. It doesn't, like, it's not like the huge, it's not like huge graphs. I just
Without using large graphs, how can we show the benefits of here? So later you can try some 1 gigabyte, 2 gigabyte size graphs.
I actually looked for it, but I think these are the largest I found for now. Like, given the time I had, I was able to find only this one. And the YouTube and Twitter are the small graphs.
If you, I I expect that the running time should be linearly increasing.
Yeah.
Linearly increasing. So if you have the large graph, it's a linearly increasing. So that's
Yeah. If the graphs here, the data sets here are bit random. Like I didn't choose them based on everything. Like I looked for two large graphs, two small graphs, just to demonstrate the effects on these types of graphs. Okay, so first we have the instant recovery strength of the PM. So what is instant recovery? So we talked about DL, which is volatile. So if a power outage happens, the whole data is gone from the DL. But the persistent memory is persistent. So we can actually store the whole data into the memory, and we don't need to care about the data loss or getting the whole data from the disk again and then map it in a CSR. So if we see the numbers, we can see the DRAM is taking much more time.
that's just a 10 second. 10 is a second or 10 seconds?
No, yeah, it's 10 seconds.
10 seconds.
Yeah.
Okay, normal, it's normal.
Yeah.
This is very slow.
Yeah. So here we are for the DRAM, we are getting the whole, we are passing the whole graph from the disk, and then we are building the CSR. So it takes a lot of time. Compared to the PM, where the graph is already residing on the PM and we just map it directly. So it takes significantly less amount of time to get the data up and running.
Okay, good.
Then we have the latency test. So we run a BFS algorithm. So basically the algorithm runs in the memory. Every caching and everything is happening in the memory. But what we test is we get the nodes, one from DRAM, one from the PM. So here we can see the baseline is DRAM, and we can see the PM is 1.59 times to 2.47 times slower than the DRAM, which is expected. The larger the graph is, the slower the operation becomes. And then finally, we have the write amplification bottleneck, where we actually keep inserting the edges one by one, and we can see the write amplification issues here. So you can see the DRAM, which is in the blue, has higher throughput considering the PM. Like the PMs are significantly slower because of the write amplification, and the DRAM is way faster. Even for the largest graph is very fast.
So insert one edge.
Sorry, one by one. We're inserting edge in every edge one by one.
Do you use some framework or just that you already have the space for the edge?
No, we just allocate the data and it's just a simple.
So I see the graph already there.
Yeah.
And it already have space that you can insert.
Yeah, we are basically inserting the same edges into a empty graphs. We are building the whole graph again.
Oh yeah, that's the way we're doing the experiment of Pickle vision. Yes, we're doing this. We skip the part of maintain the dynamic graph.
Yeah.
That's another topic. It's don't mix them together. Yeah.
So yeah, it's kind of like simulating a dynamic graph as well. We are just inserting every edge.
One not evaluating this dynamic graph inserting this.
No, we're just like it's normal basic insert operation. So with these experiments, we verified that the pros and cons we discussed earlier about persistent memories are actually true, and our
why PM is faster than DRAM?
No, PM is slower. Higher is better.
Higher is better?
Yeah.
Oh, millions of seconds per second.
Yeah, it's like million edges per second.
Oh, okay.
So yeah, that's all.
Good, good.
And finally, we have the research proposals. So what we plan is we will be using a CXL based disaggregated memory to hold the graphs. And then we will go something like a vertex centric buffering, what the XP graph used. So since the XP graph actually put all the caching into the DM, we will try to follow that approach as well, because that also cuts some latency from the execution time. And then we will try to implement the source node, the wave node algorithm, what the IO based code maintenance did, just to see if we can shorten the execution time even more. These are the proposed architecture for the code scale dynamic Keiko maintenance. And
Just there is for key maintenance.
yeah.
Okay, good.
Then we have some other research questions. So we have to adapt the Keiko algorithms for CXL latency. So we need to see if those old algorithms work, how the old algorithm works, or maybe how we need to update them based on the hardware. And then we have the disaggregation impact of separating compute from the memory. So basically, we will try to use the CXL as a memory to store the data. And like we will try to keep it discrete, so that whatever the hardware is, like there is a new generation of CXL, the algorithm can do its job without altering itself. And then we will try to we will see if we can try to come up with a generic data structure which might be usable in future implementation of other graph algorithm which might use the persistent memory.
Generic data structure which can be used for other. What kind of data structure? Generic.
So we discussed in the beginning that we will try to keep the data structure as generic as possible, separate from the algorithm, so that this can be used in other ways as well.
For example,
I'm not sure.
like a bucket. Right?
Yeah.
Bucket is used by others.
And then finally, we will our another big goal will be make it truly parallel.
Yes. You have some ideas how this parallel can solve the data racings?
Sorry?
Data racing. So two threads are accessing the same data. Data. How can you solve that?
So
So
yeah, that will be an issue, because if we have a suppose a log, then if two threads are trying to write it or read it, there might be a concurrency issue. Then we might need to create a separate locking mechanism, so that if one is doing something which might update the data, we can lock it, so that, or maybe create a snapshot of the previous one before doing its task, so that if other thread access that data, it gets actually the unedited or maybe a clean data.
It's a okay. You can talk to the lock. We're doing the lock free. Okay. Lock is very slow.
Yeah.
Lock free is much more efficient.
Yeah, I'm not aware of how if there are any
Similar.
Yeah, lock-free mechanism is there, like I'm not aware of those, but yeah, I'll try to see if we can do it lock-free.
That's good.
And yeah, this is the methodology and timeline. So the phase one is we deep dive into the hardware and we do some experiments, which is done. Then we do the K-core maintenance algorithm for CXL, and then we check the feasibility if the changes actually outweighs the benefit of CXL or not.
What is the feasibility?
Like we will check if what's the what is it called? Like what's the trade-off?
Oh, trade-off.
Yeah.
Trade-off, yeah.
Yeah, we will see if the trade-off actually the thing we did actually it outweighs the benefit of CXL. Then we have to maybe go back and update. We check how the trade-off is minimal so that we can keep the most of the CXL. Like we are not giving up too much. And then we do the benchmark for with the real world data set, maybe a large data sets where we have gigabytes of data.
Okay, good.
And yeah, that's all. Thank you.
Where do you go for presentation? Okay.